So welcome to our seminar today. Today we have Nick Foti, who's from the University of Washington. He's doing a postdoctoral fellowship with Emily Fox, and he's here to talk to us today about scalable Bayesian inference for interacting time series. Since this is a very different type of seminar today. It's more interactive. So we have the Google group going on. So if you're with us on the Google group and watching live, then you can enter in a question, which I'll be moderating, and then I'll possibly interrupt the speaker and ask that question to Nick, and he can respond. So without further ado, let's welcome Nick.
All right, thanks, Becca. Yeah, thanks for the introduction. Thanks for trudging through the snow, the weather we all expected and stuff. So yeah, today I'm going to talk about scalable Bayesian inference for time series data. And so in a variety of fields, we have access to recordings from a large number of objects simultaneously. For instance, in neuroscience, we have access to whole brain recordings while people are performing tasks. In finance, we record the price of stocks and bonds and other exotic derivatives. And even in climate science, we record things like temperature and rainfall at many locations across over the Earth. And so the goals with this type of data, at least for the purposes of this talk, are one, can we learn the interactions between these signals that we record? So in neuroscience, for instance, these interacting time series can tell us things about something like functional connectivity. So this is how the brain is implementing cognitive functions. In finance, these interactions can help us quantify risk, so that maybe we don't lose all our money when we invest. Or maybe we're actually interested in prediction, in which interactions can help. So in climate science, as we increase the temperature, what happens to rainfall in particular areas? Another problem we might be interested in with time series is capturing dynamics. All right, and so this is like quantifying the temporal dependence that we observe in these signals, maybe determining whether or not they're switching regimes of different behavior in the series, as well as other things. Sorry if this table is in the way. There are a lot of models for both interactions and these dynamical questions. For instance, vector autoregressive models or hidden Markov models in the switching regime case. And they're going along with these models. There are a lot of algorithms in order to learn the structure as well as these dynamics. But the problem in a lot of these cases is that these algorithms don't scale to the size of the data that we see in practice. All right. And so in this talk, I'm going to talk about some work addressing these issues. All right. So just some quick background on my research path. So I did my PhD on Bayesian nonparametrics, in particular incorporating covariates into random measures to be used as Bayesian nonparametric priors. And I tended to use these things to develop things like dynamic topic models, which we applied to large text corpora, or just dynamic factor models applied to financial data. However, when I finished grad school and was going to do a postdoc, I had the realization that what was keeping these methods from being applied to real applications wasn't so much our ability to specify really complex models, it was our ability to actually perform inference on them. Right? So in my postdoc, I sort of switched my focus from modeling to more computation. All right? And so first, I focused on scalable inference for Markov models, so we have large sequential data, as well as looking at the streaming case, where you get a large amount of data that comes in over time, and you don't necessarily know how much there's going to be. So also in my postdoc, I started working with a neuroscientist at the University of Washington, and in particular, looking at this problem of characterizing auditory attention and how the brain implements that. And so that sort of motivated work on looking at graphs from time series and inferring connections or interactions between time series from raw signals that we observed. And so that's the first thing I'm going to talk about today. All right, so as a motivating problem for inferring interactions between time series, we're going to look at a neuroscience example. All right, and so magnetoencephalography data is what we're going to consider here. And so magnetoencephalography, or MEG, it captures the weak magnetic field that the brain gives off while it's performing some cognitive function. Right? So basically what happens here is some unsuspecting individual sits in this hairdryer-esque machine, and we can record the magnetic field that the brain gives off while they're doing whatever they're doing at 102 locations around the brain at a pretty high sampling rate, about 1,000 hertz. So very, very good temporal resolution. However, because we're recording a field, the spatial resolution isn't very good here. We can't really localize what this sensor, or what part of the brains generate the field at this sensor, say. Right? However, there are methods that do allow us to basically do some inverse imaging from this field to a pretty detailed location in the brain. All right? And so these are the time series that we're interested in working with. Right? So we actually, for a lot of locations on the brain, say maybe going from tens of thousands down to hundreds, maybe down to tens even, we have some time series that tells us the amount of activation that location on the brain is contributing.
Yeah, quick question.
Yes.
I understand that you're interested in the regions of the brain that are active.
Yes.
But there should be less signal there than there is in the 120 sensors that you have. If you don't find nice interpretable time series structure in the 120 sensors, do you think you could find it? You would have no hope finding it in the brain.
Yeah. So it's not that there's no hope of finding it. Like the information is there in the sensor space. Mm-hmm. However, you're observing some mixture because it's from the field. And so basically, this here is just like deconvolving that mixture.
And you think that inverse problem makes it easier or harder?
It makes interpretation easier. Yes. I mean, conceivably, you could do interactions here and then do this step.
Yes.
To do that as well. That tends not to be the approach. I think that's just a design decision on their account. In that it's easier. It's just easier to do this pre-processing up front and then build your models here, because this little arrow here is actually hiding a lot of details.
I appreciate that. I probably would have decided differently.
Okay. Yeah. No, it's definitely feasible. That's a good point. Any other questions about the? All right. So for locations on the cortical surface here, we observe some time series, and then the goal is, can we somehow infer the connectivity between them, right? So the big idea we're going to work with here, there's some desiderata about these connections that we want to impose as well. One is we want to account for all time lags in our interactions. So we don't necessarily want to know that at this time here correlates with this time here, et cetera. We want, given the entire trajectory of the sequence, how do these series interact with each other? Additionally, we want the linear effects of the other series removed. So we don't just want the marginal, connection here. We want some sort of notion of conditional structure. All right. And so the idea here is, well, these desiderata sound a lot like graphical models. So can we extend graphical model structure learning to this case of time series? All right. So we're going to be Bayesian about this. And so the ingredients here are some prior on graph structures, some computationally efficient way to evaluate the likelihood of our time series given our graph structure. And then once we have that, then we can do some exploration of the posterior graph structures given the observed series. Right? And so we're going to talk about this part of the process today. There's a lot of interesting work in both the prior and posterior exploration, but this part will be pretty interesting. So just as a quick review of graphical models for IID data. So we have some graph G. We have some graph G, all right, which is made up of some set of nodes, V, and some set of edges, right? And so we say that when there's no edge between two nodes I and J, so in this case x1 and x2, then these two variables are conditionally independent given all the other variables in the graph, and we denote it this way. In the case when our random variables are jointly Gaussian distributed, so x with some covariance matrix sigma, then this conditional independence relation given by the graph is actually equivalent to saying that the ijth entry of the precision matrix is equal to 0. All right. So the graph structure is encoded in the sparsity pattern of the precision matrix. Okay. So any questions about that? That's pretty key. All right. So now what we want to do is we want to take this graphical modeling framework And instead of having each of our nodes in the graph be a single random variable, we want to allow each one to be a whole stochastic process, so a whole time series, right? And what we want to do is find some representation of conditional independencies between time series, given the entire trajectories of all the series. So for this talk, we're going to assume stationarity, so that the mean of all of our time series is constant, and the covariance function only depends on, or the lagged covariance only depends on the time difference and not the time itself, right? And for simplicity, we'll also assume that all our series are mean zero. All right, so just an overview of what we're going for. So we have our graphical model here, where each node is a whole time series, right? And so what we're going to say is when there's no edge between two of our time series nodes, then we're going to say that those series are conditionally independent, given the entire trajectories of all the others. So this is just the desiderata that I've been talking about previously. We're going to denote this way to make it clear that this holds for all lags, right? And then that's essentially what it is. So this notion here will account for all lags between interactions, and also all the linear effects of the other series will be removed. And you can sort of see this if you look at the representation of these stationary series as an infinite bar process.
Actually, if you don't mind,
yes.
Suppose you look at not all lags, but first look at all lag 1, then lags 1 and 2, then lags 1 and 2 and 3. It seems to me at some point we would have a reason for saying 3 lags is enough. Yes. And so opening the door to all lags is to complicate things.
So we're going to see that there's a really nice way to characterize this conditional independence at all lags. But yeah, so it is conceivable that you could get these very sparse, long-range dependencies in time, right? Because there is a lot of noise in these series as well. So a lot of the small lag dependencies will actually be probably just noise.
But this is sort of where I was going with that. It'd be interesting to know what is the length of the relevant lags.
Exactly.
If it's small, that's really nice. And if it's long, then you are rethinking things in a big way.
Exactly, totally. So yeah, this is just to start. Set analysis, we thought conditional independence is probably a place to start, and then we can start trying to characterize where these lags are. And because you'll see later that there's a pretty big assumption that we have to, pretty stringent conditions we have to put on inferring these lags, and that we definitely want to relax that later. I think it gets it sort of better. Sweet. Oh, now my thing doesn't work.
Try it again.
Awesome. Thank you. All right. And so basically, these two desiderata here were exactly what we had said we wanted for our notion of functional connectivity earlier. So this is what we're going to use for that application. All right. So let's just talk about a quick naive way to do structural learning. So let's take our time series and put them each in a column of matrix. So each x1 here is the activation at location 1 in the rate over time. Location 2 up to location P. All right, there might be hundreds of these, or maybe thousands, depending on how fine-grained we want to be. So what we can do is we can take those and just vectorize the matrix and stack all the series on top of each other into a big column vector. And then we'll just assume that that vectorized version of our series is just Gaussian distributed, where the covariance matrix is given by this big block matrix here, where the blocks are made up of the lagged covariance matrices that I talked about before. So the covariance between xt and xt plus h. All right. And so this is great. Now we're back into like standard Gaussian graphical model structural learning problems. There's a slight problem here. This matrix is absolutely massive. its size TP by TP, where T could be hundreds or thousands, and P could also be hundreds or thousands. Yeah?
So those covariants are all the same for each of the time series.
Which
for example, the lag. They don't have any parameter for any independent time series. Sharing.
Well, so this would be a full P by P.
Yeah, I know.
Yeah.
The gamma function, they don't have actual parameter.
Oh, yeah. So in this
all
case,
sharing the time. The coefficient you define time series.
I'm just writing it kind of generically right now. I'm not assuming a parametric form for it. So right.
Are they the same?
Yeah. So gamma H tells you how all the series interact with each other at lag H, or covary with each other at lag H. Yes. Okay. So this is a problem though, because this matrix is massive, and so just evaluating this Gaussian is really expensive, let alone really computing with it or searching over the space. So some previous approaches that are more clever than that naive approach fall into two camps. The first is parametric methods that specify some parametric model for your time series, and then basically optimize some penalized likelihood function in order to infer the structure. Some problems with this approach are you do actually have to perform model selection on your model for the series first, which also places some restrictions on the types of dependencies you can learn. And then you also need to come up with some thresholding rule as to when edges are present in your model or not. The other approaches fall into the frequency domain. We're going to see later that the spectrum of the time series actually encodes this graphical model structure, right? Whereas previous methods had to rely on these like multiple hypothesis testing type approaches to determine when there were edges, or again using some penalized likelihood, we're instead going to be Bayesian about it, but we are going to consider these frequency domain approaches. So basically, in our ingredient slide here, we're just going to, when we compute a likelihood, we're just going to replace our time domain time series with their frequency domain representations in the likelihood as well as the posterior. So that's the big idea.
Why did you prefer to do that than to work in the conditional domain?
Yeah. Well, we're going to see. There's this nice characterization of dependence there, and it allows you to be much more efficient with computations.
And this is where this result.
Well, that's the conditional how conditional dependence is encoded. The computational stuff is something we have in mind. Okay. Yeah. So just a quick review of Fourier analysis, and just to set this in notation. So we have say a time series represented in time domain, where say xgt is our recording of brain activity at location j in the brain. So what we're going to do is we're going to decompose the signal into the sum of sines and cosines, okay, where we take the sine of a particular frequency and weight it by some value, which I've depicted here. So this frequency basis function here has some large negative component in the signal. This one has a small positive component here, etc. And so we're representing our original signal as some linear combination of sines and cosines, essentially. And so our frequencies here, lambda, that we're going to deal with, are just uniformly spaced in the interval 0 to 2 pi. And our coefficients are just given by projecting our original time series onto the sines and cosines of the respective frequency, right? And so the key here is that this is actually an invertible transformation. So when we talk about looking at the probability of our series in the time domain, it's equivalent to looking at the probability of our series in the frequency domain. Okay, since we're actually dealing with multiple series, what we're going to do is we're going to take each of our series for, say, a location on the brain, and we're going to use our Fourier transform to compute its Fourier coefficients. Right? So these are all the Fourier coefficients for the first series, the second, down to the p. And then what we're going to do is we're going to take all the Fourier coefficients for, say, the 0th frequency and put it into a vector d0. We do the same for d1, do the same for frequency k, all the way up to the last frequency, t-1. And so these are all complex valued vectors in p dimensions. Okay. And so these are what we're actually going to model. So, yeah.
Do you have any parameter in this frequency domain? It seems to don't have any parameter.
Yeah, we'll get there. we'll get there. Right now, we're just taking our data and representing it in a different way. Okay. Yes. All right. So just to make the relationship between time and frequency explicit, so in the time domain, recall that the distribution over all of our time series is really governed by this autocovariance function, these gamma h's. All right. So in the frequency domain, what we're going to see is that the distribution over our Fourier coefficients is governed by what's called the spectral density matrix, which is S here, which you get by just taking the Fourier transform of our autocovariance functions. When I say Fourier transform of this matrix, I just mean Fourier transform element-wise in the matrix. All right. So we saw in the time domain that graphical model structure was encoded via the sparsity pattern of the inverse of that huge block matrix that I showed you before. So the autocovariance matrices stacked together. But how do we do this in the frequency domain? That's a valid question, which I'll talk about in a second. Additionally, we saw in the time domain that the distribution of all our series was a huge Gaussian with some massive matrix. And so the question is in the frequency domain, how are our Fourier coefficients distributed? Right? And I'll talk about these two things in a second. All right. So first, let's talk about encoding our conditional independent structure. So for Gaussian IID random variables, recall the inverse precision matrix encoded our graph. So here's this result. So for a Gaussian stationary time series, if we look at the inverse spectral density matrix, so at every frequency we have a permission positive definite matrix, right? And so what we do is we look at that given frequency, we look at the inverse of that matrix, and we look at the zero pattern in that matrix, as well as the zero pattern in the matrix at the next frequency, all the frequencies. Turns out that the two time series, xi and xj, will be conditionally independent given all the others if there's a zero in the ijth entry at all the frequencies of the inverse spectral density matrices, right? So the zero pattern in this huge sequence of matrices, T of them, encode the graphical model structure we've been talking about previously, where each of our nodes is an entire time series. Okay, so we see that in the frequency domain, graphical model structure is encoded in the inverse spectral density matrix over all frequencies. All right, so now let's talk about characterizing the distribution. So in the time domain, the likelihood of our time series, given this huge block matrix, all right? And what we want to do is we want to figure out what the corresponding distribution over our Fourier coefficients is, and it's going to have something to do with spectral density matrix. All right. So an interesting result of Brillinger in, I don't know, 70s, early 80s, was that the Fourier coefficients at different frequencies turn out to be asymptotically independent of each other. All right. So we can break this big joint distribution into this product of distributions independently over frequency, where Sk here is just the spectral density matrix evaluated at frequency lambda k. And furthermore, what's really cool is that each of these distributions over an individual Fourier coefficient is actually given by what's called a complex normal distribution, which is just an extension of the Gaussian distribution to complex numbers, or complex vectors in this case. And it has this form here, which, yes, looks strangely like a Gaussian, where dk star here is conjugate transpose. Okay. So this is really nice because we can express this frequency domain likelihood that we're interested in using what's called the Whittle approximation. We can say it's close to the product over these complex normal distributions. Yeah.
So this is when the process is stationary.
Yes.
And what's asymptotic?
As t goes to infinity. So as the length of your series goes to infinity. Yeah. Yeah. So what's really interesting about this is we converted the likelihood in the time domain, which was a full Gaussian and really very, very hard to compute because of that huge covariance matrix, to be a bunch of independent Gaussians in the frequency domain. And so now, instead of having to deal with a TP by TP matrix and compute with that, which is awful, instead we have P by P matrices, which is much nicer to compute with. All right. Was there a question?
So this argument about this
Is it convergent distribution, and no matter what, you can still use those asymptotic convergent distribution and replace it with asymptotic distribution and compute that? Is it good to compute? I didn't do this before, but it seems it's like a basis method. Do you compare these two? How different they are?
Yeah, so the Whittle approximation kicks in pretty early. So T doesn't have to be too big in order for this to be a relatively good approximation. The bigger problem when evaluating this is actually evaluating the time domain likelihood to make sure that it's right, because you have to do this huge matrix inverse.
Do you have any intuition this is compared to, for example, SBD? Those are that I can make it completely independent. I don't need any
yeah. So
basis.
Yeah. So well, I mean, SBD would be a data dependent basis, yes, right? So this is a data independent basis. So that's helpful in that regard, right? So the other thing though is that if your data is really huge, doing the SBD itself could be really hard to do, right?
SBD is bigger than T. T is pretty big.
Well, it's going to be TP something.
T times something.
Yeah. Well, it's not linear, right? So yeah. So I mean, conceivably you could do this with a different basis, but we stuck with Fourier because there's this nice asymptotic result. So
to make kind of a foolish question, the Brillinger result suggests that if you take measurement at finer and finer levels, you're making the independence happen quickly. And that doesn't quite seem realistic, because I'd imagine that if there's a minute's dependence on how my brain works, mm-hmm, then measuring at milliseconds is not going to give you better independence than measuring at tenths of a second.
Yeah, exactly. So the field that we're measuring and the processes that we're trying to measure in the brain actually are on millisecond intervals. No, it's not like the Wolf response, which actually is a slow evolving process, because stuff like that. So in this case, I think it is reasonable that being at the high sampling rate that we're at and resorting to this asymptotic result is a reasonable assumption.
So the asymptotic is not in the length of time; it's how fine the time is chopped.
It can be either. You can, as long as you're increasing T. So either it's increasing sampling rate or it's longer time horizons. Yeah. Yes. So we've gone from a full Gaussian that's hard to compute to independent Gaussians that are easier to compute. Cool. So we've filled in our last box that says the distribution over an entire time series. Well, the Fourier coefficients are these complex normals, and using the Whittle approximation, they become IIT.
I have a clarification that's something that it's just not clear to me. So from your motivating example, could you go back to why the conditional independence approximation, the conditional independence assumption is a good one to make for this type of data, because it just seems as though it wouldn't be a good assumption to make in general.
Yeah. So
I can see why it'd be convenient, but
yeah. So it's a good or conditional independence between the entire time series are good for this particular neuroscience application as an exploratory tool, because we don't really want to infer a lot of spurious directed connections between these series. Like we want it to be totally lag independent at this point, and then we also want to remove all the effects of the other series. So it's a reasonable assumption here, because we're not so much interested in predictions. We don't care that we're actually taking the future into account as well in these when inferring these things. So yeah, did that help at all, or is it still?
Sort of. So like in terms of like the going back to the motivating example, like how large does T need to be?
Yeah. So T doesn't need to be big for Whittle to kick in at all. It needs to be like 40 or 50. Okay. So our series are usually like at least 100, if not 1,000, depending on how big of a window we're looking at.
Okay.
So this part here is fine. I guess it's just answering a different question than you could ask a different question if you wanted to. It really just is from the neuroscientist perspective. They seem interested in being able to regress out all the interactions from the other series. Is that helpful?
Yeah.
Okay. So now that we know how sparsity is encoded and how to evaluate the likelihood in a reasonable manner, we can draw a lot of parallels to previous Gaussian graphical model structural learning. All right? And so just to review that quickly, what we do is we just have some prior over graph structures, POG, and then what we do is we formulate a prior on covariance matrices sigma, such that the inverse of sigma has the same sparsity pattern as our graph. So it has non-zeros where there are edges in G, and there's zeros where there aren't edges in G. And then we formulate an IID Gaussian observation model for our observations. So in the time series case, again, we're going to have a prior over graph structures. And what we're going to do now is instead of having one prior on a covariance matrix, we need a prior on a whole set of spectral density matrices, SK, k from 0 to t, or t minus 1. And this prior here should somehow enforce that the inverse of SK for all k should have the same sparsity pattern as G. All right? And so then from there, we model our Fourier coefficients as IID according to our Whittle approximation that we talked about with covariance matrix. Sorry, that should be SK. Typo. So yeah. So now what would be usually what's done in the in IID case for Gaussian graphical models, you specify a conjugate prior for sigma here, and it's well known that this is what's called the hyper-inverse Wishart prior. Right. So in the time series case, what we're going to do is specify a complex hyper-inverse Wishart prior distribution because our SK matrices are Hermitian positive definite instead of just positive definite. Right. So given that we have if we have a conjugate prior here, and that means that we can formulate a marginal likelihood of our data, which we're going to represent with Fourier coefficients again, given just our graph structure. So we've gotten rid of all this huge set of spectral density matrices. And then once we have this marginal likelihood here, this is basically a score for our graph. How well does our graph represent our data? And then we can basically just use existing graph structure search algorithms that are out there. This is a pretty well-studied field. However, we can also sort of automatically get any advances that are made, such as via parallelism or submodular approximation type algorithms. So being able to integrate out this matrix is very, very helpful. So let's just talk about how to do that quickly. So what we're going to do is we're going to specify our complex hyper-inverse Wishart distribution on a Hermitian positive definite matrix sigma. So sigma here would be one of our SKs in the previous slide. And so this prior is made up of a couple terms. There's a normalizing constant here, and then there's some term here that is basically a Wishart distribution, just extended to complex numbers. And then there's some constraint set here. So we're restricting sigma so that sigma inverse has the same sparsity pattern as our graph G, right? And so from the previous slide, we put a complex normal distribution on our Fourier coefficients. So D here would be one of our DKs from the previous slide. Remember that has this form, which looks strangely like our prior. And it turns out we can actually analytically marginalize sigma out and just get the probability of our Fourier coefficients given our graph G, which just taking the usual integral, and we recognize that this term here is just 1 over the normalizing constant for a complex hyper-inverse Wishart distribution, where we've updated centering matrix W with our sufficient statistic, updated some degrees of freedom, and we still have the same graph structure. Okay. So we see that our marginal likelihood of our Fourier coefficients given our graph is just given by this ratio of normalizing constants. All right. And so I've shown you what it looks like for one Fourier coefficient. Now we have our marginal probability here, which for all of our Fourier coefficients just looks like this. So because we use the Whittle approximation, we can just factorize over them all. And so I should also note that each of these normalizing constants can be computed relatively efficiently. In general, they just involve taking the determinant of your centering matrix WK and some product of gamma functions. But because we factorized, we can take advantage of parallelism. So we don't actually have to. We're not taking t times as long for the IID case. We can get some speed up. And additionally, if you actually restrict the set of graphs that you look at, you can actually come up with algorithms that allow you to do fast updates for these normalizing constants as you add and remove edges from your graph. So we're going to take this framework that we've talked about, and we're going to apply it to some neuroscience application, in particular analyzing some MEG data from an auditory attention task. And so the goal in this study is to uncover the functional connections, basically the cortical dynamics between brain regions underlying these auditory attention tasks, right? So this is important for a couple of reasons. One is to gain insight into cognitive disorders. The one we care about in the lab is called central auditory processing disorder. However, it's conceivable that these types of methods could also be extended to things like autism. Additionally, there's some opportunity for potentially making engineering advances here for things like smart assistive devices for people with these disorders. So the way the experiment works is as follows. We lure some victim into the MEG machine, and then we play them 2 streams of sound, all right? And they're told while listening to these sounds to either maintain their attention on one stream or to switch to the other stream. And these streams can either be spatial, so that one's left and one's right, or they can be based on pitch, where there's a high pitch and a low pitch. Right? And so we record that information, we record the magnetic field again, and we use our machinery to localize those signals on the brain, resulting in these time series at different locations. And so for this study, we had 10 subjects and about 10 to 50 trials per subject. And each trial in this case will result in a 50-dimensional time series. So we took our really high resolution spatial model of the brain and downsampled it a lot to get 50 regions that we cared about for this task, right? And so we have our 2 tasks, maintain or switch, across either pitch or space, right? And so what we did in this case is we actually averaged all the subjects and all the trials for each condition, or for each combination of maintain in pitch, maintain in space, or switch in pitch, switch in space, in order to smooth out the signal a bit. And so here I'm showing the edges that we learned consistently in both tasks, all right? And so these are taken from map, like the map solution of a lot of runs. And so you see a lot of similar structure, a lot of local structure, as well as a little bit of long-range structure. However, on the bottom, I'm showing edges that we learned only in one task versus the other. So in red, we see edges that were only learned in the switching task, whereas in black, we have edges that were only learned in the maintain task. All right? And so these look like hairballs. But what's interesting is that in the switching task, at least, we do see a lot of extra front-to-back behavior. Not so much there. And so basically, these pictures, when we showed them to the neuroscientists, they got more excited than we expected them to, because kind of parabolic pictures. But basically, they're very interested in sort of taking these models, making them more sophisticated, in order to tease out some of this local structure, because they don't believe that really exists. But to figure out what part of this sort of front to back structure is actually true. Okay. So that was sort of encouraging. And additionally, we've talked about how to maybe incorporate some of these connections that we're seeing and figure out if we can update the experimental design to try to tease out the signal. Yeah.
So your model, in a sense, compares Fourier modes of different bit signals, right? Yeah. Is it good assumption in these applications? Because Fourier modes are very global.
Yes. So that's a great question. So further to be an edge, or further to not be an edge in this graph, it basically we need independence across all frequencies, right? And so that's a really, really strong assumption. And so we'd love to relax that assumption a little bit. But because we're being very strict in that regard, we actually are being a little bit conservative about when we're actually inferring that there's not an edge, right? So we're more certain in here about where we're not seeing edges than we are at this point. And so I think at the end of the day, it's not a great assumption, and we're working on ways to relax it a lot. I think it's a good first pass as an exploratory tool.
Do you have any idea on the how this model perform as a hypothesis testing? Like,
Yeah, we're not certain yet. We developed it for exploratory purposes for now. Hypothesis testing in this field is a little strange, and I think there's some other questions that we need to get at before we try to hypothesis test. Like, we probably want to take inter-subject variability into account in order to actually get an idea.
yeah, and I guess what I meant was like what it means for there to be edge given there is really strong assumption.
Yeah.
Can you like are you detecting a lot of things that are probably not real? Or?
So I didn't go into it now, but the prior we use on graph structure is supposedly lowers the number of false positives that you look at as you introduce more and more goods into the network. So we take some hope that hopefully that's helping us, but there probably are a lot of false positives in here now, and we need to make models slightly more sophisticated to scrutinize.
So I have a question based on that. So I know you haven't done anything with regards to hypothesis testing, but you've mentioned things with regards with basically edges that are there and that aren't there. So in terms of just like your exploratory analysis, have you looked at something like a false negative rate and a false positive rate to see like at a first step how well or how not well you're doing?
Yeah, so in synthetic data.
Okay, yeah.
But obviously not in the real application.
So can you say a little bit about that?
Yeah, exactly. We find that, so we've looked at a couple different settings. One is as t increases, where you only have like one observation, as well as in the case where you have, say, n observations, and we look at how these rates change in both of those conditions. We find it as you increase n, your true positive rate goes to 1, same with increasing t, and your false positive rate has a weird shape to it, actually. Here, we'll draw it this way. It does go down as you increase n and t, but you have this sort of false zero for very, very small values where you're basically learning zero edges. And then all of a sudden you start learning edges, your false negative rate bumps up, false positive rate.
Okay. And so do you have any idea why it's basically going up and then coming back down? So you said it's going like this.
Oh, yeah, because early on you learn zero edges, and so you don't falsely predict.
But do you know like why it's peaking at a certain point?
Yeah, because that's where that's where you had enough data to actually say that there was an edge.
Okay, and so is that consistent across like the different synthetic data sets that you're looking at?
Yes.
Okay.
Yes. I can show you.
Okay, yeah, that'd be great.
Yeah,
thank you.
Definitely. Okay, so just as a quick review, motivated by this problem in neuroscience, we wanted to infer the conditional independent structure that existed between time series, right? And so we wanted to take all lags into account and remove the linear effects of the other series. And so this corresponded really nicely to a definition of functional connectivity with these neuroscientists. We saw that there was a convenient representation for this conditional independence via the inverse spectral density matrix, where the sparsity in these matrices encoded that conditional independence, just like in the IID case. Then we looked at this hyper-complex inverse Wishart distribution as a prior over these spectral densities in order to marginalize out spectral density matrices and lower the number of parameters we needed to learn, right? We applied this to some MEG data, and we actually saw that there was some task-specific structure that got some neuroscientists excited, and we'd like to interrogate more. So we talked about graphs of time series, and when we have a lot of time series figuring out how to interact. However, this isn't always the right problem for time series. Often we're given one extremely long time series, and we're actually interested in, say, characterizing the dynamics in that series. So detecting whether or not there's switching regime such that the time series behaves differently in those different regimes, which leads into what I'm going to talk about next, is a scalable inference algorithm for hidden Markov models. All right, so to motivate this work here, let's consider the problem of segmenting some human chromatin data. So we have this chromosome data set from the ENCODE project at UW. We have a sequence with different locations on it, and at each location, we have a 12-dimensional real validated observation. Right? So the goal here is to segment our sequence into basically biologically relevant functions. All right, so we're looking for things like promoter elements or transcribed regions or repressed regions. And so we're going to use an HMM or hidden Markov model for this problem. But the difficulty here is that the length of this sequence is like 250 million observations. Standard algorithms for HMMs just are not going to scale to this because it turns out that just representing the data, it's about 24 gigabytes of data. And so traversing that once is hard, let alone traversing it multiple times.
Well, if you model like time series, like forward backward, those are linear.
Yeah, but linear and 250 million.
But you can still do it separate.
Well, you can, but there's some problems with that, right? So we'll get there.
You don't need to do the inverse.
Yeah, you don't have to do the inverse. But even the forward-backward algorithm, it's too expensive in this case. Yeah. So just as a very, very quick review, in an HMM, we observe observations along some sequence. Could be time, could be location on our chromosome. And associated with each observation is some latent state that can take on one of k categorical values. All right. And then theta here are, say, the global model parameters. So these are the transition probabilities between the latent states, as well as any parameters that the distribution of our observations need. So if our observations are Gaussian, we'll have a set of means and covariances in theta as well. All right. So, and so I'm just not going to draw the arrows because the pictures get really messy. So when we want to do Bayesian computation in HMM, we're interested in the posterior distribution, obviously, of our latent variables and our parameters given our data, right? And so most algorithms basically iterate two steps. One is called a local step, where you update your beliefs about the latent variables or the local variables, because there's one per observation. And then, given your local step, you perform what's called a global step, where you update, or given your beliefs about the latent variables, you update your beliefs about the global parameters. Right. So we're going to talk about variational inference for HMMs. How long do I have also? We started a little late. So,
yeah, so probably about 10 more minutes.
Okay, cool. So in our variational inference algorithm, what we're going to do is we're going to assume that our full posterior here factorizes into a distribution over our latent states, which is independent of a distribution over our global parameters. Okay? And so notice that we're going to retain structure in our latent state. We're not, so there's still temporal dependence or just dependence between these variables, as opposed to breaking all of those dependencies as well. And so the game now becomes, let's find the best approximation to our posterior in our tractable family. And so how we're going to do that is we're going to minimize the KL divergence from our approximate distribution to the true posterior. Okay? And so it turns out minimizing this KL divergence corresponds to what's called maximizing the elbow, which is the evidence lower bound, which is given by this quantity here. It has a term to explain the data well, and it has a regularizer that says don't collapse your distributions to be the data. Okay? And this is the elbow because this actually is a lower bound on the marginal likelihood of y given data. All right, so let's just quickly review how we would do batch variational inference for an HMM. So what we're going to do is we're going to hold fixed our variational distribution of the global parameters, theta. Then we're going to pass these messages forward in the chain. And these messages here correspond to basically the filtering distribution. So the probability of our latent variable given all the previous latent variables and observations up to time t. Okay. Then what we do, given those messages, we pass messages backwards in the chain. And these messages correspond to the predictive distribution of all future observations given our latent variable as t takes on a particular value. Given those two messages, we can compute basically any statistics we need about our local variational approximations. So in this case, say the marginal variational distribution that xt takes on a particular value, just given as the product of alpha t times beta t. And then basically given those statistics, we can update our variational distribution of the global parameters by following, say, some gradient of the elbow with respect to our distribution of the global parameters. Okay, so that's batch BB for HMMs. However, the problem with this is that the cost is actually order k squared t. K squared is the number of latent states that you have, and t is the length of your sequence. And so, like you're saying, The cost complexity of the time complexity of this is linear in T, but T is so massive that it's really impractical to be linear, right? And so this is really costly if you, say, initialize your variational distributions randomly, where you have a lot of observations that are just redundant and don't provide very much information to your gradients. So what can we do about this? Well, the naive method would be to take our really, really long chain here, to split it up and treat each of these subsequences as IID. We'll pass our messages forwards and backwards along each subsequence, and then basically what we'll do is we'll take the statistics from all of these these small chains and use them to update our global variational distribution, Q of theta. Now, a big problem with this is how do you choose how to split these series? You have to do it a priori, so you may not have a lot of information about your chain. If you make it too short, you might miss some important dynamics in your chain. If you make it too long, you're going to waste resources. Regardless, you're going to be doing order K-square T work anyways. It might be in parallel, but you're still doing it. So if you're running this on Amazon EC2 or something, you're going to pay for order K-square T computing per iteration. So what we want to do is to try to avoid this. So alternatively, let's break the dependencies adaptively, right? So instead, what we're going to do is instead of splitting the chain a priori, what we're going to do is subsample some xt and some subchain around it. We denote this xs. Then what we do is we do a restricted local update just on what's in the subchain, and then we compute a noisy estimate of the gradient of the elbow using just these local beliefs. All right. Now, there's some questions about what's going to happen with the algorithm. We broke these dependencies at the endpoints of our subchain. So what's the result of breaking these? How much are we paying in the wrong, or how much of a wrong answer are we getting? And then the big question is, does the resulting algorithm still converge? So let's talk about the first thing first. How much error are we incurring? So on the top, we have, say, the true beliefs of our latent variables, and on the bottom, the approximate beliefs had we just passed messages within our subchain here. You can see here these approximations are pretty bad, right? So let's just we're going to check and see they're bad. Let's just add a buffer of an observation on each end, and then let's pass messages within the buffered region, but then only use what's in the red box for our gradient updates. Well, we can see that when we've added our buffer, our approximations to the local distributions have gotten much better. Are they good enough? Well, maybe they're not good enough. So we add another buffer, or another buffered observation, pass messages in here, and we see that, oh, okay, these approximations here are pretty close to these local beliefs. So if we compute gradients using these approximate beliefs here, then they're going to be pretty close to gradients had we used these true beliefs up here. Right? And so the key here is that we only need to consider some small buffer around these subchains. Okay? However, in practice, we don't actually know those true beliefs that I had up there. So we actually just use some greedy heuristic where we grow the buffer out until it doesn't change very much. And we find that this buffer never has to grow very big, and it also actually it leads to good behavior in the algorithm. We see that it converges well. Talking about convergence, it turns out that if you perform a global update using these buffered subchains, then the iterates of that algorithm will actually converge to the local mode of the elbow in the limit. And basically the intuition here is, here's the true gradient with respect to our Q theta of our elbow, had we used the full data set, and say, here's the gradient had we used a buffer length of 1, here's buffer length of 5. Basically, the longer the buffer is, these gradients will converge to the true one, and so you can see the algorithm converge. So we applied this method to segmenting this human chromatin data set. Again, 12-dimensional observations using an HMM. So previous work by Hoffman et al., they developed a pretty sophisticated dynamic Bayesian network in order to do this. And so what they ended up having to do was the naive thing I talked about, which was break the sequence into a lot of independent pieces and then perform EM in parallel on each. And so this severed some long-range dependencies as well as still wasn't very computationally efficient. So what we did instead was we used an HMM, so a much simpler algorithm, and used our buffered SBI algorithm on this data set. And so what we found was we were able to achieve a lower false discovery rate of promoter elements, which is what they cared about in their work with the dynamic Bayesian network. We used a simpler model and still achieved comparable results to them. And we didn't have to arbitrarily break these dependencies, nor did we have to do as much work as they needed to do in each of their parallel iterations. So one of the big things here, though, is their algorithm took days to run, whereas ours took less than an hour to run in this data set. So we just talked about the case where we have one huge, long time series. But this isn't even that descriptive of all data sets. And the next question is, what do we do when data arrives over time and we don't know how much there's going to be? So this is the so-called streaming setting. And so examples of this abound. The fire hose that is Twitter data, wearable sensors, medical records, Facebook activity. All of these generate a large amount of data in time, and we don't necessarily want to have to go back and refit our entire model every time a new observation arises. Okay? So what do we do? So just to formalize this, we want to update our posterior beliefs in our model parameters as new observations come in from this stream. All right? So we're going to work in what's called the assumed density filtering framework. So we're interested in some posterior distribution of model parameters given n observations. So the way this works is, assume we have, say, a variational approximation given the data up to the n-1st observation, right? So when a new observation comes in, what we're going to do is we're going to compute some candidate posterior by incorporating it into the model, all right? And then what we're going to do is, because that candidate distribution probably isn't in our variational family, we need to project it back onto our tractable family by minimizing this KL divergence here, all right? And then when another observation comes in, we basically do the same thing. So the way you can really think about this is just Bayesian update with this extra projection step, because we have to have a tractable family for our posterior. Okay. So what we did is we applied this to Bayesian nonparametric mixture models. So Bayesian nonparametrics are actually really well suited to streaming, since they can adapt their complexity as data comes in. So there have been some existing streaming approaches for the Dirichlet process before. So what we basically did is we took one of these existing approaches, cast it in this ADF framework, and we were able to extend the algorithm to a more flexible class of mixture models based on what are called normalized random measures, which basically allow you to specify more interesting tail behavior of your partition than the DP allows you to. So the key to this algorithm here is that you only need to keep running a running sum of soft assignments of observations to data points, as well as sufficient statistics for your components. You don't need to actually remember the entire partition, nor do you have to go back and update it. So that's the key to making that work. We applied it to document clustering a large New York Times data set, which I'm happy to talk to you about offline. All right, so just to recap and summarize, so I talked about 3 lines of work in modeling and computation. So looking to the future, though, I'm really motivated by this neuroscience work, this collaboration I have on auditory attention, specifically coming up with models to infer functional connectivity. However, sort of addressing this problem of characterizing auditory attention is going to require a lot of developments in a variety of areas of statistics and computation and whatnot. And the ones that I'm sort of most excited to work on imminently are, first of all, how do we account for sort of unobserved series? So we're getting a whole brain recording, but we're really not recording everything. There are gaps in our sensors. We're actually only getting neurons that are aligned in a particular way. So the signal that we're actually seeing is actually just a part of something that's more complex. And so how do we sort of tease out connections that only exist because we're really only observing a mixture, even in the location space that I talked about previously. Additionally, I'm interested in developing models for time frequency analysis. Essentially, neuroscientists are very interested not only in capturing interactions within frequency, but also across frequencies as well, because they think that this might be how the brain actually implements a communication network and sends messages. So I think models for that are sort of understudied right now, and actually could have applications beyond neuroscience as well. So these types of models are actually going to drive some computational work as well. They're themselves very, very big. They have a lot of frequency components, a lot of time components, a lot of latent components in the unobserved case. So whereas my original computational work has been on scaling to the amount of data that we see, what I'm interested in now is actually scaling to the size of models that we're interested in doing inference for. So the first line of work along in this area is inference for structured objects like graphs or for spectral density matrices in the time frequency case. Another line of work in this area is on asynchronous algorithms. So instead of parallelizing over the data, we're interested in parallelizing over the model, splitting it up into multiple machines in order to speed up inference. And then finally, in order to make these algorithms applicable beyond just my problem, I'm trying to frame them within the larger context of useful systems for data analysis, right? And so part of this is sort of taking advantage of and also contributing to languages that allow us to easily specify complex models in order to easily iterate them, as well as when I do computational work to make them somewhat generic and scalable so that they work well for a reasonably large class of models and not just tailored to my specific problem. With the big goal of this to actually just be to create data analysis tools for scientists to efficiently iterate their data science loop of specify a model, fit a model, and evaluate a model first so that I can answer my questions in my neuroscience application, but also so other people can answer their questions as well. So that's all I have. Thanks for coming.
Yeah. I think that you were in the segmentation problem. You were determining the buffer size that you needed adaptively. Mm-hmm. But it seems to me that in the Markov model, you would be shifting from regime A to regime B, or regime A to regime C. There's some sort of finite number of different regimes. Yes. As you obtain your data, your prior that you are switching from A to B will get updated, and you may think this is now very likely. Yeah. And I imagine that for any specific pair of regimes, you could figure out how large a buffer you need for that transition. Yeah. Yeah. And so there's the potential to, instead of sort of brute force adaptively, fill out your window until it stops changing. Yeah. Instead, say when I'm 90% certain that I'm looking for a shift from A to B, I know that I don't need a buffer size larger than 5. Yeah. And call the shot that way. Yeah. Yeah.
So we've looked at more global versions of that idea in the sense of there are some bounds for essentially hidden Markov models and how quickly they forget. Mm-hmm. We haven't been able to make them useful yet because they tend to require some constant, which is essentially some bound on the likelihood that if we restrict it, maybe we can make it useful, but it essentially just makes the bounds trivial, unfortunately. So that's an interesting idea, though, looking at it pairwise instead of maybe at the same time. Yeah.
So I have a question about your variational approximation, which I think is very nice. Do you have some thoughts about extending it, for example, to basically relaxing, for example, a normality assumption, or to moving past just categorical and past Dirichlet processes in terms of handling a more general case of just general data? So if you think of Facebook data, or if you think of electronic health data, then it's continuous, it's messy, it's both continuous and categorical. Do you have thoughts on?
So this is for the streaming one?
Yeah, for the streaming.
Okay. Yeah. So the way it is right now with the mixture model, obviously that predicts the project step is very, very nice for the categorical part. Yeah. That gets harder for other distributions. If you want to be continuous, Gaussian is really what you want to be. Although mixture of Gaussian might be reasonable. So you could have a model that uses mixture of Gaussian emissions to get it maybe something on Gaussian if you wanted to.
Yeah, but if you think about electronic health data, yeah, or even Facebook data, a lot of the data won't have that nice Gaussian or mixture of Gaussian
Yeah. Are you talking about marginals, or are you talking about the whole?
The whole thing, or even just the marginals. If we think about data of that form, it's not really going to have a Gaussian distribution.
Yeah.
And so a lot of those assumptions won't be valid. And so I just wonder if you have thoughts on on maybe like looking at mixtures of Gaussians at first, or just other types of models that might fit in that framework?
Yeah, I mean, you can specify whatever model you want in there. The question is just computationally, how easy is that project step?
Sure.
And so, unfortunately, outside of categorical variables and Gaussians, it gets a little tricky. What we usually end up doing in that case is just switching the KL, and that makes it computationally tractable again. But that actually has pretty bad consequences for streaming, because that's the case where you start underestimating the variance. And so when your Qn-1 has already underestimated the variance, it's very spiky. So when you try to predict later, you're not predicting very accurately, essentially, right? And so essentially your model just collapses to this like bad solution, essentially. And so I've seen this happen with HMMs. We've tried this framework with it. So the way I'm actually going with the streaming stuff is there's actually this very nice connection between Bayes' theorem and what are called proximal point algorithms, which are these sort of convex optimization algorithms to find the maximum of a convex function. And so you can see when you formulate Bayes' theorem in that way that basically a lot of your evidence is put on the first few observations, and it's like very hard to forget those observations. Okay, so what we're sort of looking at now are sort of modifying proximal point iterates in order to put more weight on current evidence. Okay, and still this doesn't help us with our non-Gaussianness, but at least it helps us with sort of we could do VB updates instead of these scale P to Q. And hopefully, because we're weighting more recent evidence more heavily, that we're not going to fall into this problem where we use VB and we collapse on this bad solution. We can at least maybe maintain ability to actually learn something as time goes on. So I guess the moral of that story is just we're looking at actually changing what the update is in order so that when we can use approximate computational steps and still be able to learn something. So, did that kind of answer what was going on?
Yeah, sort of, yeah.
Okay.
Are there other questions? Okay, well, there weren't any online, so...
They could hear me online, right?
Yeah, they could hear you. So let's thank Nick, and there will be other meetings tomorrow. So
cool. Thank you.
Oh, Mike just asked a question. Mike just asked a question. I can't read it. Hold on. Okay, I'm going to ask a question from Mike. Speaking to the basic use underlying the... Oh, Mike's not good. Can you put us back online, boss?
I am online. We haven't...
Oh, we're still going?
Yeah.
Okay, thanks. Okay, so I'm going to ask a question from Mike West. So, speaking to the basic use underlying the use of the Whittle likelihood in any context, and particularly in your kinds of neuro applications, sorry, this is very hard to read. The approximation is bad unless t is very large, and as t increases, your data is going to be far from anything we'd agree is stationary. One core question is how far from stationarity can you go before it all collapses? So I think I'll let you answer that, and then I'll continue with the rest of Mike's question.
Well, I mean, we're assuming it's all stationary, so whether or not that's a bad assumption is obviously up for debate. But Yeah, I'm not exactly certain how far from I mean, it obviously assumes everything is stationary. So as soon as you deviate from stationarity, you're going to be in trouble. We've obviously tried to make our series as stationary as we possibly can, but in this framework, it's sort of an assumption that we're stuck with, and we just need to hope that it's good for now. And that's why we're working further. We're developing further models in order to try to not have to live in this.
Okay, then to interject as Mike would, then how are you assessing whether this is an issue at all? So for example, assessing whether the data even looks close to stationarity. So maybe with respect to the FFT summarizes you were using. Also, in your example, you said you averaged over subjects and conditions. Are you not then averaging out all the action?
So we don't think that so we're not looking for the interactions and the trends of the series, which is what we'd be averaging out, right? We're looking for interactions in the residual of any trends in the signals, right? And so that's really what our connections are getting at.
So I think what Mike means here is he mentions issues of registration of the origin timescale and dealing with the subject and condition specific effects.
Yeah. So this data set was very preprocessed so that it should be time locked. So the origin, so that they should all essentially be aligned as to when the stimulus was happening.
I'm just asking Mike if he has a follow-up question.
Okay.
He says, okay, thanks, no more today. Okay, let's thank Nick very much.
Thank you.